All right, today we're having a look at expanding grouping symbols that involve surds. Now, a little recap for you. Hopefully this is a recap, not new learning. If I've got something like this, x outside of x minus 2, I can expand that to give x squared minus 2x. This x here is a factor of both x and minus 2. So we end up being able to multiply and have an ungrouped set of terms. Now, if I've got something like this, a binomial, x minus 3, x plus 5, well, I can split my first set of brackets there, and I'll end up with something like x outside of x plus 5, minus 3 outside of x plus 5, x squared plus 5x minus 3x minus 15. Simplify the middle terms there because they're like terms. X squared plus 2x minus 15. If I've got something like this, x minus 3, x plus 3, we call that a difference of two squares because we've got the same two terms, but one is a sum, the other is a difference. I've got x squared, and it's exactly the same as the second one I've shown there, x squared plus 3x minus 3x, which gives me 0, and then I've got x squared minus 9, which really is x squared minus 3 squared, and we can simplify that fully to x squared minus 9. The last one to have a look at before we actually look at the surds here, even though this is a surds video, something along the lines of x plus 4 all squared, which is x plus 4 multiplying x plus 4, so we call it all squared, which gives me x squared plus 16, so x squared and 4 squared, and then twice the product in the middle. So that's 4x plus 4x is 8x. And of course, I could go and write the expansion here of x plus 4 plus 4, x plus 4. You might use FOIL or draw your ski jumps on there, however you're doing that. As long as you know how to expand these four types of expressions, you're good to go. Now, what we're going to do here is rather than having just constant terms and pronumerals in here, we're actually going to have surds in here as well. But overall, the things we're going to do are exactly the same. Okay, let's look at a couple of examples here. Okay, so we've got 4 examples here, and what we're going to see is that they're actually largely similar to the algebraic ones we've just done. So my first one here, my root 2 is a factor of both root 2 and 3. So I'm going to end up with root 2 multiplied by root 2, which is just 2. Or how I got there is to say I've got root 2 times root 2, which is root 2 squared. The squared and the root are inverse operations. They cancel each other out. Or we could go along and say, well, if I've got two roots multiplying one another, I can say that's the root of 2 times 2, which is the root of 4. That's 2 as well. However you're getting there, as long as you can recognize that root 2 times root 2 is 2, you're good to go. Plus 3 times root 2 is just 3 root 2. So we're using our multiplying techniques a lot here and possibly some simplifying as well as we go through. All right, so here I've got 4 things multiplying one another. 1, 2, 3, 4. I'm not going to write out the first bracket expander, but you can if you would like. So root 2 times root 2 is just 2. Minus 3 root 2 plus 1 root 2, which is just root 2, minus 3. So if we have a look here, my like terms are my constants, and then of course my root 2's as well are like terms. So what I'll end up with is 2 minus 3 is minus 1, and minus 3 root 3 plus, minus 3 root 2 plus root 2 is minus 2 root 2. Again, you'll see it's very similar to the algebraic questions we've been dealing with as well. Here I've got a difference of 2 squares. Now, we know that the middle term for a difference of 2 squares is going to collapse. If you're still saying, oh, I'm just a little bit sketchy on getting that, you can write out the four terms here and see that the middle ones collapse. I'm going to show you the quick way to do this. Root 5 multiplied by root 5 is, in fact, what I will do is I'll write out the full expansion. I've got root 5 being squared minus 1 root 5, which is just root 5, plus 1 root 5. I'm calling it 1 root 5 because I'm showing you that the 1 and the root 5 are multiplying, but 1 root 5 we just call root 5. And then, of course, minus 1 squared at the end, which is just minus 1. So root 5 all squared is just 5. And you'll see these guys in the middle here, they are equal but opposite, property of difference of two squares. So I'm left with 0 in the middle. 5 minus 1 is just 4. Now this one here is a special result. Okay. When we use a difference of two squares like that, it's what we call root 5 plus 1. The conjugate of that is root 5 minus 1. And that's something we're going to use later in a couple of lessons' time to have a look at rationalizing fractions, rationalizing the denominator of fractions. It's a really useful process when we're trying to add and subtract things from one another. But for now, if you can see that if we've got a difference of two squares, it's going to give you a whole number result, a rational result. That's a good result for you. It wouldn't matter, by the way, if it was root 5 plus root 3 and root 5 minus root 3, kind of like the last one is here. We would still get a whole number, a rational number, when we expanded that out fully, if it's a difference of two squares. Now, of course, root 5 plus root 3 all squared, meaning I've got root 5 plus root 3 times root 5 plus root 3. You can write it that way if you would like. So the terms I'm going to be left with, root 5 times root 5 is 5. And then from here, I'll get root 5 times root 3, which is root 15. Then root 5 times root 3 again is root 15. Plus root 3 is just 3, or root 9. So I'm left with 8 plus 2 root 15. Now I've got a surd that's not a prime number, so I should have a look and see if I can simplify it. I can't because my factors of 15 are 5 and 3, nothing that I can simplify there, no square numbers going into that. So we've got our 4 ways we can expand things here. A single set of brackets, a binomial, a difference of two squares, or a perfect square. If your algebraic skills are good, this should be just an extension of that, including some of those surd skills in there as well. I hope this has been helpful.